AP Calculus AB, Unit 6, Day 15, Office Hours. This is the pretest, so this is going to be a really good review for your upcoming test, which is also our first semester final. So let's take a look. You're going to have to do some problems like this, where I just give you a picture of the graph and you identify these special points and intervals. This is about as straightforward as it can get. Horizontal tangents, just clarify what appears to be horizontal tangents are horizontal tangents or something close. That's sort of a corner there. So the roots are when f of x equals 0. So I'm writing some little notes here if you want, just to remind you of how we find these things. So these are x coordinates. X equals A, C, F, and H. Those are x-intercepts, right? Roots. Critical points are where the derivative equals 0 or undefined. So that's 0 slopes. So we have those ones. We have B, E, and I, peaks, valleys, plateaus, but also sharp peaks. That's where the slope is undefined. So we're going to add G to that list. Inflection points are where concavity changes. So concave up, concave down, concave down, concave up. So you're like, well, is it C or D? Well, C is a root, so it's probably D is the intent. And you got to check a cusp. This goes from down to down, so it's not this time, but it could be in the future. I. Okay, stationary points are where the slope is specifically 0 only. So we listed those earlier with critical points, but we're going to leave G out. So it's going to be B, E, and I. Relative extrema, that means relative maxes and mins. Extrema includes both of them. So we're looking for where f prime changes signs. I mean, on the picture, they're peaks and valleys. So we could do relative maxes are at x equals E, just E. Relative min occur at B and G. The sharp one counts. Intervals of increase. So that's where f prime is positive, going up. And we include endpoints. So we're going to say B to E, brackets, and G to H to I to J, G to J. Don't break it up because we include endpoints, so we might as well just keep it all together. If you break it up, I'm taking off points. Intervals where f prime is increasing. Well, that means the derivative of this is positive, so we're looking for the second derivative to be positive. So that's associated with concave up. And so I would say A to D. Now, usually we don't include endpoints for concavity, but no one said anything about concavity. They said we want to know where something is increasing. So we do brackets whenever we talk about anything increasing or decreasing. And then I to J. So we're doing brackets because of the wording of the problem. Okay? Because it's increasing. Absolute extrema, those are absolute maxes min. So the absolute max is at x equals E. The absolute min is at x equals, it looks like B, but watch out for the endpoints. So there's a bunch of points right there. Quick points, not a lot of work, but don't mix them up. Don't forget points. There's easy ones to miss. And so unfortunately, some people will lose points there that hopefully they wouldn't. Now the next one, we're using the graph of the derivative. The graph of the derivative. So this is f prime. Okay. So f prime. If you treat this like the regular graph, I'm not giving you any points for the answers. You're going to be way off. So I would say, okay, well, f prime is negative, so it's decreasing. F prime is positive, so it's increasing. F prime is negative, so it's decreasing. F prime is negative, so it's decreasing. This is a critical point, critical point, critical point. These are also stationary points because their slope is 0, right? So the x-intercepts of the derivative graph are critical points. Concavity is the derivative of the first derivative, which would be the slope of this graph of slope. So the slope of the slope, the slope of this graph is the second derivative, is positive concave up. Second derivative is negative concave down. Second derivative is positive concave up. Second derivative is negative concave down. And the inflection points are going to happen in between those where the concavity changes. So I think I have probably about everything I need. Well, we could say that this right here is a relative min because you're going down and then up and then up and then down. This is going to be a relative max. And that's going to be neither. It's a plateau because we're going down, flattens out, and then we keep going down. So there's no peak or valley there. So where are the relative mins at? Relative min is at x equals 1. Relative max is at x equals 3. I have all the answers on my picture. Inflection point at x equals 2, 4, and 5. And then intervals where f is decreasing. So that's negative derivatives. So that would be 0 to 1. We include the endpoints for increasing, decreasing. 3 to 5, and then 5 to 6. So you should just do 3 to 6 all at once. Don't break it up. Don't go 3 to 5, 5 to 6. If you did, it's the same thing if you have brackets, but it's just unnecessarily broken up. So I want nice, clean, simple answers. Let's see if we can draw a sketch of the original graph from the derivative graph. So we've done a lot of this. We have all the information we need from the work we did before. So I'm just extending these lines to make it a little easier. We're going to start some arbitrary point, except that we've told that it starts at f0 is 2. So first chunk is going down, but concave up. Down, but concave up. Next chunk is up and concave up. Next chunk is up, but concave down. Next chunk is down and concave down. Should be a nice smooth graph from one piece to another. Next one is down, but concave up. And next one is down, but concave down. So something like that. All right. Let's see. Which of the 5 points of the graph do dy dx and the second derivative have opposite signs? So I think we had some problems like this out of the book before. So here, dy dx is positive, and here, dy dx, the slope is negative, and here, dy dx is negative. It's going down. Here, I'd say dy dx is 0. And here, I'd say dy dx is positive. And we're looking at the original graph. In concave, this is all concave down, so f double prime, or the second derivative of y, is negative. And this is concave up, so the second derivative of y is positive. So where do they have opposite signs? Well, this one's positive and negative, so I'd say A. Okay. B, negative, negative, same sign. C, negative, positive. So C, they have opposite signs. D, positive, positive, so not D. So A and C. This one says sketch graph where all these things are true. So I would try and put as many things on here. So f1 equals 3 tells you for sure that point's on the graph, right? And it says f is increasing everywhere except for x equals 1. Okay, so it's positive slopes everywhere except for x equals 1. The second derivative is positive for x less than 1. So it's concave up over here and concave down over here. And it's continuous. So it's got to be concave up and increasing. And then I think maybe what's happening, and then it's got to be concave down and increasing. So I think what's happening right here is that we're getting a vertical tangent. That's why f is not technically increasing there, because it's infinitely steep. So something like that. All right, function analysis from equations. So we're doing it from the original graph, we're doing it from the derivative graph, and now we're doing it from the functions themselves. So we're going to be doing a lot of line checks here. Gotta watch out for domain issues. So, well, true false here. It says all critical points are extrema. Is that true? Everywhere that f prime equals 0 or undefined, it's for sure a relative max or min, or absolute max or min. What do you think? What about the plateau idea, where you have a flat f prime equals 0 critical point, but it's not a peak or a valley, right? So that's a perfect example, counterexample as to why this is false. So when you say something is false, a lot of times you could use a counterexample, something that meets the first part but violates the other part. No extrema can be both an inflection point and a stationary point at the same time. Can you have an inflection point and a stationary point? And it says extrema. So, I mean, what we just did right here, this is also a stationary point and it's an inflection point, right? Concavity goes from down to up. But that's not extrema, so that's not what we're talking about. If you did something like this, so usually the smooth ones, the critical points, stationary points, are flat, and they're extrema, and they're not inflection points. So the only other issue would be like, well, could I maybe do something where it changes concavity at a cusp? So that's an inflection point, and it's an extrema, and it's a critical point, but it's not a stationary point, right? And this one was not an extrema, and this one was not an inflection point. So I would say true. And I've kind of gone through the different scenarios. Okay, on what intervals is this below the x-axis and concave up? Now, you're definitely gonna get some problems like this with rational exponents, and they have their own potential, pitfalls. We're looking for below the y-axis, so that's when f of x is just negative. So we're not doing derivatives yet. This is an uncommon question because it's not as deep. So we could just go ahead and set this equal to 0 undefined right now and do a line check with the original function. Now factor out the GCF, which would be 3 and x to the 2/3. We always factor out the smallest exponent of x. And when you do, you're using rules of exponents. So you're going to subtract that from this, and you're going to get 3/3 minus 5. And so then we're going to get x equals 0 and x equals 5, because that's just x to the first. These are zeros, right? We're looking for zeros. These are roots, x-intercepts. Now this one has an even root on the top, so that guy is going to bounce off the graph because of the even numerator. If the denominator is even, that's not an issue, but that could be a domain issue. Or is there any issues with domain here? We should be asking ourselves on every one of these problems, are there any issues with domain? None, all reals, right? The domain is negative infinity to positive infinity. So we're good on this problem. Now the line check looks like this, 0, 5. Don't forget that bounces off. Test the value, x equals 6. Positive, negative, negative. I like to draw these little arrows. Decreasing, decreasing, increasing. Relative min. Actually, you know what? I messed up. This is not the derivative, so no arrows here. This is below the x-axis, below the x-axis, above the x-axis. So we want to know where's it below. So I would say negative infinity to 0, break it up, union 0 to 5. I would not include these endpoints because it's not below the x-axis, it's on the x-axis, those points. But usually we're going to go into derivatives and second derivatives. So concave up is where the second derivative is positive. So we've got to find the first derivative, which is going to be power rule 5x to the 2/3 minus 10x to the negative 1/3. I'm doing a little bit of work in my head. I don't need to find critical points, so I'm going directly to the second derivative. This is going to be 10/3 x to the negative 1/3 plus 10/3 x to the negative 4/3 This is what we're going to set equal to 0 undefined to find potential inflection points. So I'm going to factor a 10 thirds x to the negative 4 thirds out, smallest exponent. That's going to make this x to the positive 3 thirds because you're going to subtract negative 4 thirds from negative 1 third, which means you're going to add 4 thirds to negative 1 third, and you get x equals 3 thirds plus 1. Now undefined is coming from this guy, and 0 is coming from this guy. So we get x equals negative 1, and we get x equals 0, but be careful, it has an even numerator, so that guy is a repeated even root. So this right here is specifically an inflection point. This one is not an inflection point because it's going to bounce off the graph. So you can tell if they're inflection points before the line check, but you should still put them on the line check. So we're going to test the value, x equals 1, positive, positive, negative. This is the second derivative, concave down, concave up, concave up. This is an inflection point. We don't know where's the concave up. So we're going to say negative 1 to 0, parentheses, we don't include the endpoints. You have to break it up at 0 for concavity. So there you go. That's the work. Be careful. Okay, number 8, find the relative extrema. So we need to find critical points first. We're going to take the derivative, label it. Derivative cosine is negative sine. Leave the inside the same. Times the derivative of what's inside is 2. Plus derivative of x is 1. And then we're going to set it equal to 0 undefined. This is all stuff you should show in your work. So then now if we solve for sine x, sine 2x equals, you're going to subtract 1, divide by negative 2, it's going to be positive 1/2. Alpha equals pi over 6 is that first common angle. 0, 1/2, root over 2, root over 2, 1. Angles are 0, pi over 6, pi over 4, pi over 3, pi over 2. I just memorized this in those separate orders. We're in quadrants 1 and 2. So 2x equals, quadrant 1 would be pi over 6 plus 2 pi k. And quadrant 2 would be 2x equals 5 pi over 6 plus 2 pi k. I'm going to divide by 2. And so x equals pi over 12 plus pi k. And x equals 5 pi over 12 plus pi k. And then we specifically want all of them between 0 and 2 pi. So that's pi over 12. That's 5 pi over 12. But I think we're going to get more. So because that's another 12, that would be 13 pi over 12. Least common denominator. And 17 pi over 12. These are all still within 0 to 2 pi. So we're getting 4 critical points, which kind of makes sense. We usually get 2 critical points, but because the 2 inside, that cuts the period in half, and so we get 2 periods worth within 0 to 2 pi, where we used to only get 1 period. We do a line check, label the line check, put these in order. I'm going to put the endpoints on there in order, left to right, clearly labeled. Okay, let's test a value. Tell me what you're testing. I'm going to test 0 because it's not a critical point. So sine of 0 is 0. It's going to be positive. No bounces off the graph. If sine or cosine equals plus or minus 1. Does sine or cosine equal plus or minus 1? If they do, before you solve, then those are going to be that bounce issue. So positive, negative, positive, negative, positive. So it's increasing, decreasing, increasing, decreasing, increasing, increasing, decreasing, increasing, decreasing, increasing. This is a relative min. This is a relative max location. This is a relative min. And this is a relative max. So we wanted all relative extrema. That's relative maxes and mins. So the relative max is at. You want to emphasize at. Don't say is, because they'd be the y value, which you could find if you want, but you're not being asked to, so might as well not do extra work. But you got to word it right. Relative max is at pi over 12 and 13 pi over 12. Relative mins at x equals 5 pi over 12 and 17 pi over 12. So that's why you would show your answers. That's why you show your work. So good old relative maxes mins, lots of line checks here. You're not being asked to justify them right now. So be glad about that. Now I want to find the relative max of this. So we got to find the derivative first, and that's going to be a product rule. X squared times derivative e to the negative 2x is e to the negative 2x times derivative what's inside. Chain rule, negative 2 plus e to the negative 2x times derivative x squared is 2x. And we're going to set this equal to 0 undefined. Now I think I'm just going to try and factor this out. I can factor an x, a 2x, and an e to the negative 2x. And then that would leave a negative x here and a plus 1 here. So x equals 0 and x equals 1. This isn't going to give you anything. These are your critical points. We're going to do a line check. We're going to put them in order left to right. We're going to test the value. X equals 2. Positive, it's going to be negative, positive, negative, decreasing, increasing, decreasing, decreasing, increasing, decreasing. This is a relative min, and this is a relative max. We're looking for the relative maximum. So the relative max, this is a location, but it says find the relative max. So that's the y value. So you gotta be careful. We need to plug this back into the original equation. And so that's going to be e to the negative 2, which maybe we don't want negative exponents for our final answer. So this is the max. That's a relative maximum. So, we could word it, relative maximum is 1 over e squared at x equals 1. It's kind of a little more of a thorough answer. So lots of points from these kind of problems on your test. That's the majority of the points is this kind of stuff, these line checks. So show your work, nice and neat, label things. So here's some more on what intervals is this function above the x-axis decreasing, conjugate up, has 0, has relative extreme. So above the x-axis, we would just factor the original graph. We'd say, well, let's take an x to the 2/3. Smallest one would be x to the 3/3 left over minus 10 equals 0 undefined. So that's going to be 1. So x equals 0 and x equals 10. These are your zeros. And that one is going to bounce because it has an even numerator. So then we're going to do a line check with this. 0, 10, tests, x equals 11, positive, negative, negative. So below the x-axis and above. So if we want to know where it's above, we would say 10 to positive infinity. Do not include the endpoints. Okay, decreasing. So above the x-axis is just when the original function is positive. Decreasing is when the derivative is negative. So let's find the derivative f prime of x equals 5/3 x to the, if you subtract 3/3, you get 2/3 minus 20/3 x to the negative 1/3 equals 0 undefined. I'm going to factor this. So we can take a 5/3 x to the negative 1/3 out, smallest exponent. That's going to leave you with x to the positive 3/3 because 2/3 minus negative 1/3 is plus 1/3 is 3/3. Minus 4 equals 0 undefined. Again, we need to be watching out for any domain issues. So were there any domain issues here? No, it was all reals. Nothing causes problems here. Any domains here? Domain issues here? No. Good. Any domain issues here on the original function? Nope. No negative exponents. No even denominators, which would be even roots, which have problems. So x equals 0 and x equals 4 are your critical points. So then we do a line check. And we're going to test a point, 5, x equals 5, everything's positive, negative, positive, so increasing, decreasing, increasing. So we can, and relative max here, relative min here. Now, so it says, where is it decreasing? So it's decreasing on 0 to 4, include the endpoints as long as they're inside the domain. So that is B. Okay, C says we can answer E, but now concave up, so I'm going to find the second derivative. That's going to be 10 ninths x to the negative 1/3 plus 20 ninths x to the negative 4/3 equals 0 undefined. You factor it, you take out a 10 ninths x to the negative 4/3 smallest exponent. This is going to give you x to the 3/3 plus 2. Usually it works out really nice if you factor out the right thing, like on the inside of it. That's just a 1, so that's x equals negative 2, x equals 0. This is an inflection point. This one is not an inflection point because that even numerator in the exponent. So it's going to bounce off the graph. So then we're going to do a line check, label the line check, -2, 0, test a value, x equals 1. So that's going to be, everything's going to be positive, positive, negative. So concave down, concave up, concave up, concave down, concave up, concave up. This is an inflection point. So let's see, concave up would be -2 to 0, union 0 to positive infinity. You have to break it up at 0. We don't include endpoints on concavity. Got to break it up. Now zeros, we've already found these. The zeros are at x equals 0 and 10. We found that up here. And then the relative extrema, the relative max is at x equals, we already found that somewhere, relative max right there, x equals 0. Relative min is at x equals 4. So we found those there in that work. Lots of good stuff. Okay, the maximum value. It said the max. If it doesn't say relative, that's absolute. It doesn't have to say absolute, but if it doesn't, that means absolute. And this also means that we're looking for the y value. So be careful here. The maximum value. They didn't say where or the x coordinate. Now you have endpoints. That's one of the conditions of EVT. We want to do EVT for sure. Do EVT. We need to find the critical point. So we got to take the derivative, set equal to 0 undefined, factor it. Oh shoot. We can take a 6x out, so it's going to be, nope, sorry. We take a 6 out. That'll make things a little easier. And then factor at x minus 2, x minus 1. So x equals 2 and 1. So these are critical points. So then we're going to make a table. And we're going to plug these back into the original equation. So -1, 1, and 2. So one of the critical points ends up being an endpoint. Who cares? If any critical points are outside the endpoints, don't calculate. So I plug -1 in here. I get -2, -9, -12, -1. Negative 11, negative 23, negative 24. If I plug 1 in, I get 2 minus 9 plus 12 minus 1, so that's negative 7, that's 5, that's 4. If I plug 2 in, I get 2 times 18 is 16 minus 36 plus 24 minus 1, so that's negative 24. That's 3. So here's your min, here's your max. So the max value is 4. Derivatives of logs and exponentials. So we're trying to find the derivatives. Y prime equals, we got to do a little product rule here. X cubed times derivative of e to the 2x is e to the 2x times derivative of what's inside is 2. Got a little chain rule there. E to the 2x times derivative of x cubed is 3x squared. And then we should clean it up. 2x cubed e to the 2x plus 3x squared e to the 2x. There you go. Next one, the derivative of this is going to be 1 over what's inside. And then you got to multiply by the derivative of what's inside. Derivative of an exponential is itself, like e to the x, but then you got to multiply by the natural log of the base. And then chain rule says you got to multiply by the derivative of what's inside, secant squared. Ooh, that's kind of ugly. Now these cancel out. So we get something kind of nice. Natural log of 5 secant squared x. Or alternative is you could have used log rules right at the beginning and rewrote this as tangent x times natural log of 5, and then just take the derivative of this. Now, natural log of 5 is just a number, so it just stays in front. You don't have to do product rule. Derivative tangent squared is secant squared. Hey, wow, that was a lot easier than the same answer. Something to consider. Log rules, right? Let's use log rules now. Let's break this up. Do you really like quotient rule, or do you like avoiding it? All right, we can bring this 2 out in front. Just got rid of a power rule, chain rule. I think that's all we can do. So I would take a derivative of this. 2 over x, natural log of the base. Now the base of a regular log, common log, is 10. Minus 1 over what's inside, 1 minus x squared. Need the natural log of the base. Chain rule says you got to multiply by the derivative of what's inside. So final answer, 2 over x natural log of 10 plus 2x over 1 minus x squared natural log of 10. And that's fine. This one, we're going to do it implicitly, but we could use log rules right away to make it a little easier. So that would be natural log of x plus natural log of y squared equals e to the 2y. We could bring this 2 out in front. Natural log of x plus 2 natural log of y equals e to the 2y. And then take the derivative implicitly. Derivative with respect to x of natural log of x is 1 over x plus 2 over y, but then you got to follow it up with a dy dx, which, by the way, is what you're looking for. Derivative e to the 2y is e to the 2y. Times derivative of what's inside is 2 dy dx. This is what we're trying to get by itself. So we could move those terms to the other side. So we have a 2e to the 2y minus 2 over y. Then we divide both sides by this. Now, these are pretty messy, complex fractions, so I multiply top and bottom by the least common denominator of the top and bottom to get rid of the fractions inside the fractions. So dy dx equals y on top, right? And then 2xy e to the 2y minus 2x on the bottom. I'd say that's your best answer. Got a couple more good ones on the back. So, I mean, I don't we've seen this enough. We've seen these enough to think that maybe we should just rewrite it without negative exponents right away, right? And then get rid of the fractions and the fractions right away. Because then you're going to get e to the 4x plus 1 over e to the 4x minus 1. And taking care of that is going to be a lot easier than what we started with. But you could do it with what we started with. I'll go ahead and do it the hard way. So this would be quotient low d high, e to the 3x times derivative what's inside is 3 plus e to the negative x times derivative what's inside is negative 1. Low d high minus high d low, 3e to the 3x plus e to the negative x, all over low squared. So it's a bit of a mess. I mean, we got to FOIL all this out. So it's going to be 3e to the 6x plus e to the negative 2x minus 3e to the 6x. I don't even think I finished that up. 3e to the 3x. I don't even do it all. 3e to the 6x minus e to the 2x minus e to the 2x plus e to the negative 2x minus 3e to the 6x plus e to the 2x plus 3e to the 2x. I missed. Show a 3 here. Plus e to the negative 2x. Then you distribute this subtraction all over e to the 3x minus e to the negative x squared. And this was just a mess. These guys cancel. These guys cancel. And it turns out to just be e to the negative 2x. So, I mean, we could write that if we're okay with all the negative exponents. Otherwise, I think I might have made a mistake somewhere. Oh, yeah, this should be negative. These guys don't cancel each other out. Or yeah, -4 and then another -4, so it's -8. So that'd be your answer, but we could try and rewrite it without negative exponents. And now the bottom was squared. You might want to go ahead and multiply this out. E to the 6x minus e to the 2x minus e to the 2x plus e to the negative 2x. Should be 1 over e to the 2x. So we can multiply the top and bottom by e to the 2x. And you would get -8 over e to the 8x minus 2e to the 4x plus 1. You got some different options, but there you go. Or you could try the easier way. No negative exponents, no fractions and fractions. It's a lot cleaner. This one right here, I would use log differentiation. Log differentiation. And so that's where we say, well, let's take the natural log of both sides. And use log rules to break it up, because it's going to make it a lot nicer. This is going to be natural log of e to the sine 2x minus natural log of cosine x squared of x squared minus 1. We could take this further, bring this out in front. Sine 2x, the natural log of e is 1 minus parentheses natural log of cosine x plus natural log of x squared minus 1 to the 1/2 power. You got to make sure you distribute all this though. So we get natural log of y equals sine of 2x minus natural log of cosine x minus 1/2. I'm going to bring this out in front. natural log of x squared minus 1. So I haven't done any calculus yet. There's just a lot of algebra there to break that up. So now if I take derivative, it's going to be 1 over y dy dx equals cosine 2x times derivative what's inside is 2 minus 1 over cosine x times derivative what's inside is negative sine x minus 1 half times 1 over x squared minus 1 times derivative what's inside is 2x. So 2's are going to cancel. I want to get dy dx by itself. So I'm going to multiply both sides by y. And y is just what we started with, e to the sine 2x over cosine x, square root of x squared minus 1 times all this stuff, 2 cosine 2x plus tangent x minus x over x squared minus 1. I mean, it's pretty ugly, but it's better than the alternative. So, inverse functions. If f of 7 is 3, so 7, 3 is on the original function, then we know that 3, 7 is on the inverse function, right? So if f7 equals 3, and the derivative, so f of 3 is going to equal 7, and the derivative of that 3 is going to be the derivative of 7 upside down. That's it. Find the equation of the tangent line to the inverse. So this is the old school, new school way. I would do new school. So new school says, you know what? Let's use that slope and just flip it upside down. But here's the thing. X equals 6 is on the inverse graph, which means that y equals 6 is on the original graph, which means if I plug it into the original equation, I can figure out what the x value should be on the original graph. So I factor it. Now we should only get one answer if it's a function, so that's where this comes in. We only want the positive one this time. Said negative, we put the negative one. So now we're going to take the easy derivative of the original function, super easy. We're going to plug the correct x value in to get an easy derivative. And then that means that the inverse at 6, which corresponds to this one on the original graph, is just going to be that slope upside down. That's it, upside down. And here we're trying to find the derivative. So this is just another derivative. Now this is a rule that one of the last rules we covered here. So the derivative of inverse cosine of u is negative 1 over the square root of 1 minus u squared, and then you got to follow it up with a du dx. So this is a rule that you got to memorize, and we're using it here. So y prime equals negative 1 over the square root of 1 minus whatever's inside squared times the derivative of what's inside. So that's going to be 2 to the x natural log of the base. So your final answer is negative 2 to the x natural log of 2 over the square root of 1 minus 4 to the x if you simplify it. I mean, you could say 2 to the 2x, but that's the same as 4 to the x. Okay, find the equation of the tangent line. Equation of the tangent line. So we need the coordinates. So we're going to plug this in. Negative 1 to the 4th power. So that's inverse tangent of 1. So what you're asking yourself is, what would I take tangent of, what angle to get 1? And I think of as 1 over 1 because it's sine over cosine. And I'd say, well, how would I get 1 over 1? Well, that would be from root 2 over 2, root 2 over 2 having the same angle. So alpha equals pi over 4. And it's going to be quadrant 1 or quadrant 3. So that's theta equals pi over 4, or it equals quadrant 3 would be 5 pi over 4. So that's that's our point. We need the derivative, so y prime, the derivative of inverse tan is 1 over, so the derivative of inverse tan is 1 over 1 plus what's inside squared, and then of course the derivative of what's inside squared. Usually there's a chain rule there. So this is going to be 1 over 1 plus x to the 4th squared times derivative of what's inside be 4x cubed. So y prime equals 4x cubed over 1 plus x to the 8th. And then we need to plug -1 into this to get the specific slope. So that's going to be -4 over 2, which is -2. So that's your slope. So in point slope form, y minus pi over 4 equals -2 times x plus 1. Equation of the tangent line, point slope form is totally enough. Of course, that's it. You are going to have one of those motion graphs that was on some of the other worksheets on assignment. Yeah, so there we go.